Hi, ladies and gentlemen. This time, let's talk about petroleum and petroleum fuels. Now, first off, where did petroleum come from in the first place? It is very often referred to as fossil fuels, and that is exactly what it is. These are fossilized remains of living organisms. And where did they come from in the first place? Well, they came from photosynthesis. Probably the most important chemical reaction that exists on planet Earth is photosynthesis. And this is this process whereby light from our fabulous star interacts with water molecules and carbon dioxide gas in our atmosphere and fixes hydrocarbons in the form of sugars and carbohydrates and produces oxygen. And this is how our planet got an oxygen-rich environment many, many, many millions of years ago that set the stage for you and I to be here. But in this process of doing this, this created these hydrocarbon molecules in the form of these small living creatures. So what was the ultimate source of all of this? Well, the ultimate source was the sun. Remember that law of conservation of energy. You don't get anything for nothing. And so the sun has been dumping energy into our planet for millions and millions and millions of years. And that has been stored in our planet in these hydrocarbon molecules. Now, what happened to those little critters? When I was a child, I remember my family members sitting around saying that crude oil was dead dinosaurs. And I remember even as a kid thinking, how the heck do they know where all the dinosaurs went to die? I always thought that was a pretty funny thing. Well, there were not that many dinosaurs. Most petroleum and natural gas deposits are actually small dead sea creatures that came from the ocean floor. Tiny, tiny, tiny marine plants and animals. And through time, they died. These little tiny marine organisms, they died. They fell to the bottom of the ocean floor. Through time, sand and silt that deposits in the ocean fell on top of them and squeezed them. Well, the hydrocarbon molecules that made up these complex molecules of life that made up these animals through millions and millions of years got broken up into hydrocarbon molecules. And a lot of heat and pressure under the rock turned this into liquid. And this liquid mixture of a variety of hydrocarbons is what we today refer to as crude oil. So where do people mine for crude oil? Where do they drill for crude oil? It is found in places that used to be seafloor. So in the United States, vast areas of the midsection of the country used to be under the ocean when ocean levels were much, much higher. And that's why Texas, Oklahoma, up into the Dakotas, Wyoming, that whole area, great oil country because of the fact that that was ocean bottom at one point in time. The upper Midwest, Michigan, Ohio, those areas that also happen to be under the seafloor at some period in time, also some oil deposits there. Coal, another fossil fuel, is primal forests and bogs. Coal is different. This is woodlands, and these woodlands were put under fresh water, and that fresh water prevented total decay and just made the woody products actually condense down into a different hydrocarbon mixture that is more close to being solid. And so not exactly the same areas, but similar, and that's where we mine for those things today. Now, when petroleum is brought out of the ground, it is this rich mixture of hydrogens and carbons, some very short chains, some very long chains. But how do you separate this out? It's separated by a process that is called fractional distillation, and it's done in something which is referred to as a distillation tower. Many of you may have driven by a place like this. A petroleum refinery looks something like this, lots and lots of towers. It's very impressive looking, and you might go, what's going on there? But when they heat it, the different chains of hydrocarbon actually separate based on size. The more volatile, lightest gases have a tendency to go to the top, and the heavy, thick molecules have a tendency to fall to the bottom. And they are separated into different sizes, and each portion is referred to as a fraction. And so often this is referred to as fractional distillation. Now, if we take a look at a distillation tower, what'll happen with that crude oil, very often heated to about 750 degrees Fahrenheit, the short chain hydrocarbons, those methane, ethane, propane, butane, 1 to 4 carbons in long, those are going to be gases at these temperatures, and they are going to be siphoned off as gases and be sold as natural gas. Then the longer chain hydrocarbons are going to be separated, and they're going to go to different altitudes in this tower and be siphoned off into different pipes to the side to allow them to be used for different purposes, because they each have different properties. Kerosenes, commonly referred to as jet fuel, can be used for heaters in homes, and you might have a kerosene heater you use in your garage. These typically carbons of about 12 to 16. Diesel fuels, a little bit longer chain hydrocarbons than kerosene. You get a little bit longer chain hydrocarbons, you're going to end up with those motor oils. Then even thicker still, you're going to end up with fuel oil, tar, things that are used in candle wax. So these are very goopy, thick things. And then the bits that are quite long chain hydrocarbons, close to being true solids, they're going to go, they're going to fall down to that bottom, and those are road tar. So that there's like nothing goes to waste. It gets separated out from those tiny little carbon chains to these crazy long carbon chains. And the longer they are, the goopier they get and the more entangled they get. Now, when you burn any of the hydrocarbons, they go through a combustion reaction. A combustion reaction releases stored energy. So you've got a mixture of hydrogen and carbon, burns in oxygen. The products are carbon dioxide, water vapor, and some energy is released. These are exothermic reactions. Very similar to digesting. If you have ever paid attention and a car in front of you pulls away at a stop sign, you may have noticed coming out of the tailpipe of the car in front of you, when it accelerates forward, you might see a few drops of moisture. And those drops of moisture are water that is a byproduct of that combustion reaction. So it is very similar, combustion and digestion. Digestion, you eat the hydrocarbons, you breathe in oxygen, you exhale carbon dioxide, you evaporate out water vapor, you urinate out water, and this energy powers your body and keeps you warm. So where does air pollution come from? Well, the most abundant elements in living things make up schnapps. Now, carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus. When fossil fuels are burned, the carbons and hydrogens have this nice, pretty, clean reaction that produce carbon dioxide and water vapor. But what happens to the nitrogens, the sulfurs, and the phosphorus? First off, where did they go in the first place? A lot of the nitrogen, sulfur, and phosphorus are in all of the other tissues in your body. These are in amino acids. These are in your proteins, your DNA, your muscles, your hormones, your enzymes, all of the other molecules that make you, that make life possible. So living things are not just hydrocarbons. We are complicated, big, messy molecules full of lots and lots of other things. So in crude oil, you are going to have not just hydrogen and carbon, you are also going to have other impurities. And these impurities are not going to be taken away just because it turns into oil. So when those hydrocarbons are burned, those impurities are going to be present. That is just, they're there. They're sort of not what you want to be there, but they are there. So the extra nitrogens and sulfurs that are in that crude oil, just because it once was a living thing, when they get burned in oxygen, produce nitrous oxides and sulfur oxides, commonly referred to as NOxes and SOxes, because these can be nitrous oxide, nitrous dioxide, trioxide, nitrous oxide singular, sulfur oxide, sulfur dioxide, sulfur trioxide, etc. Now, nitrous oxides, when you see them as air pollution, very often they are a brown haze over a community. If you see a big town or a big city and there's a brown haze covering that area, that's brown, that is nitrous oxides. Nitrogen compounds tend to make brown compounds, and that's what the nitrous oxides will do. And it is air pollution, plain and simple, and it is not pretty. The sulfur oxides tend to react with oxygen to make sulfur trioxide. That then reacts with plain old ordinary rainwater and makes sulfuric acid. Sulfuric acid is sulfuric acid. That's battery acid. But this battery acid is falling out of the sky, and the battery acid causes tremendous damage to plant life. And can really destroy forests and streams and ponds. A lot of statuary that has been around for hundreds and hundreds of years, all of a sudden you pour battery acid on it out of the sky, and it is being eaten away. And it's being eaten away because of this acid that's coming out of the sky, just as a byproduct of burning petroleum. So how do you reduce it? Well, some smokestacks, and this has become by law, this is regulated, big companies that are burning a lot of petroleum products have smokestack scrubbers. Smokestack scrubbers very often contain a lot of limestone. A lot of limestone is calcium carbonate, and that calcium carbonate will react with the sulfur compounds, and they will produce a sludge to take the sulfur away and produce clean gases that are going to come out. So this is going to produce a precipitate that is going to remove that sulfur and take it out of the way. Catalytic converters in your car are going to take those NOxes, that brown gas, out of your automobile and prevent those from polluting the atmosphere. And it's also going to reduce the carbon monoxide. We'll talk more about catalytic converters in a later talk this chapter. But one of the other byproducts of a combustion reaction is carbon dioxide. It's just one of the things that gets produced. And carbon dioxide is a greenhouse gas. Now, what that means is it has a tendency to hold heat. Our planet not only takes heat in from the sun, it also gives it back to the outer space. And our atmosphere holds a certain amount of heat in. If you want to pay attention to it, pay attention to a clear night. Very often clear nights tend to be cold and cloudy nights tend to be warmer. And the cloudy nights tend to be warmer because of the fact that the clouds in our upper atmosphere have a tendency to hold that heat next to the earth, and so it holds that heat in. Well, carbon dioxide will hold in heat just the same way that a cloud layer will hold in heat. Carbon dioxide will do the same thing. Greenhouse gases in the U.S. include carbon dioxide, methane, part of that methane production from petroleum, nitrous oxides from automobiles, and fluorinated gases from cooling systems. These things help hold in that heat. So this actually warms the Earth's atmosphere. And we have to, and we are, as a humanity, looking for alternatives to fossil fuels. And we need to do this for multiple reasons. One, we are like a bunch of spoiled children. Millions of years, the sun has been shining on our planet, giving us these wonderful resources. And in the last 200 years, we've been spending this bank account like there is no end. But there is an end. And there is only a limited amount of stored energy in those mines. And the second thing, for the health of our planet, the health of our atmosphere, we have to look at alternatives because there will be an end to fossil fuels. And in the meantime, we are pumping a lot of CO2 into our atmosphere and not 100% sure of what all of the effects are going to be. So we'll come back later and we're going to talk specifically about energy in molecules. See you later. Bye-bye.